Hello everyone, welcome to the third lecture of this module 2, which is also the second week of this course on measurement and instrumentation, and we are discussing the classification of analog meters. So we are trying to understand analog meters from different perspective, and we have classified the analog meters from different angle, and one of the perspective was based on the principle of operation of these instruments. So the analog meters were, say, moving coil, moving iron, electrodynamic, induction type, electrostatic type, thermal type, Hall effect type and chemical type. Some of the effects is known from their name itself, say for example Hall effect type. So you can say that the device is based on Hall effect. Okay, but some of the instrument or some of the analog meters name is like, say, moving coil. So from its name it is not very much clear that this is based on what kind of principle. Okay, so let's see that we will discuss about these analog meters in more detail in the coming weeks. Okay, but it's very important to understand the principle of operation of these devices. Okay, so the analog instruments are classified according to the principle of operation used to convert an electrical signal. The signal can be either current or voltage depending on what it is measuring, okay, into a mechanical deflection. So mechanical deflection, basically here what I mean is the torque. Okay, so what this principle based on principle of operation means that the effect that I want to know, okay, the effect based on which these instruments are categorized. Okay, so in general the equation can be like deflection torque. I will let you know what I mean to say about this. Okay, is equal to some function of electrical quantity. This quantity can be, say, current, okay, or it can be, say, voltage, okay, or it can be a combination of these two, say for example power or say energy. Okay, so what I mean to say is any of the analog meter, irrespective of what type it is, okay, what it will have is it will try to measure certain current or voltage. Okay, say there is a current flowing, say I. Okay, because of this current I, there will be certain effect, okay, because of which there will be a mechanical deflection on a scale. Okay, so there is a pointer. Okay, because of this current flow or the voltage drop, okay, the voltage drop, there will be a deflection of this pointer. Okay, so we have to understand that what is the effect or what is behind this deflection. Okay, so when there is a deflection means that there is certain force acting on it. Okay, and when there is a force means there is a torque. Okay, so that's why I am mentioning this torque and I am denoting it as TD, as deflection torque. All right, so this is the deflection torque, and this deflection torque is because of certain effect. All right, so based on the principle of operation, as I have suggested that these devices can be categorized, and we have to understand the basic principle behind them. Okay, so let's go one by one, and the first is, say, moving coil. Okay, the moving coil instruments are based on the magnetic effect of current. Okay, so when a current carrying coil is placed in a magnetic field, it experiences a deflecting torque. Okay, and this torque is directly proportional to the current flowing. Okay, so consider that, say, I have a magnet setup. All right, I have a magnet setup where, say, this is a north pole and this is a south pole, and then we have field lines. Okay, say there is a field lines. All right, and I have, say, some coil. Okay, say this coil is wound on certain material. Okay, say this is a material on which there is a coil wound on it, okay, and say certain current is flowing through it, okay. The torque, of course, this is placed in a magnetic field, so it will experience certain torque, and the torque is directly proportional to the current flowing. All right. So this is based on the magnetic effect of the current, okay. These devices are mostly used in for DC applications, okay, because when the torque is say in the positive hype cycle, say for example, if I am applying certain say sine wave, okay, this is perfectly sine wave that I am applying, okay. So the torque in the positive half cycle is cancelled out by the torque in the negative half cycle, okay, and this result in a average torque that is 0 over a complete cycle. So there is no such movement recorded for AC voltage. You can also understand this from the perspective of say the pointer's movement, okay. So say this pointer is moving, okay, say you have applied certain say current, okay, because of which there is a magnetic field and there is a force, and because of that there is a torque, and this pointer is moving, okay. Now you have reversed the voltage or the current. Now this pointer should deflect in this direction, okay. Now if you keep on applying this AC current, okay, this pointer should go back and forth at its 0th position, okay. Now if the frequency is very high, okay, because of the inertia it will just rotate at or just move to and fro along this 0 position, and if this is very high, in fact the movement will be negligible, okay. So you will not be able to identify this. So these devices are not useful for AC signals, but they are used for DC measurement, okay. However, these you can use a linear scale for the measurement, and the devices are or these analog instruments are having good accuracy, okay. All right. The application of these moving coil instruments are in simple DC voltmeter, the ammeters, particularly the DC one, and the galvanometers. All right. So this is a type of instrument, the moving coil instrument, okay. We will discuss in more detail in coming modules, okay. Right now what we are doing is we are trying to just understand this from the principal point of view, okay. Second kind of instrument is a moving iron instrument. Moving iron instrument are the very simple instrument or analog tools, okay, and they are based on either magnetic attraction or magnetic repulsion, okay. So when a soft iron piece is placed in a magnetic field which is produced by a current carrying coil, iron becomes magnetized and experiences a force of attraction or repulsion, okay. So consider that you have say magnet or say electromagnet, okay, which is formed by this current carrying coil, okay, and you brought a soft iron bar, say soft iron bar, okay, near to this coil, okay. What will happen is this will be magnetized, okay, and when this will be magnetized, it can be attracted or it can be repulsed. Mostly it will be attracted towards it, okay. And when you have this attraction force between them, okay, you can attach, a pointer to this magnet, okay, and based on this movement, okay, your pointer will deflect, okay. Say if it is attracting, this magnet is going this side, okay. So I am drawing it over here, okay. When this is attracting, this magnet is going to this side, okay, means that your pointer will have a deflection, and when this magnet is getting repulsed, okay, so the movement of this bar will be towards this side and this will have a opposite movement. Okay, means that there is a movement in the pointer based on the interaction between this electromagnet and the soft iron. Okay, and the deflection can be detected by a pointer. Fine. So please note that you are using a soft magnet or soft iron. I am using a word soft iron. Okay, so you have hard magnets also. So hard magnets basically retain their magnetization even you remove the external magnetic field. Okay, so even if I am not using, say for example, this soft iron piece, if I am not using, what will happen? Even if I will remove this, the attraction and repulsion will not start if this material is, say for example, of iron. Okay, or say this is also having certain magnetic field. Okay, or say magnetic effect. Okay, this will be permanently magnetized. Okay. So these hard magnets have high coercivity. Okay, they exhibit a broader hysteresis loop because of this higher magnetic coercivity and other factors. Okay, that's why they are suitable for permanent magnet application, but not in such kind of applications. Okay, so these we have intentionally used soft magnetic material because they can be easily magnetized and demagnetized. So once you have excited this coil, okay, there will be a magnetic induction in this bar. Okay, and once you have reduced the current, accordingly the magnetic behavior of this soft magnet will also change. Okay, so they have a low coercivity. Okay, and they have a narrow hysteresis loop. If you compare it with hard magnets, they have much narrower hysteresis loop. Okay, and that's why these kind of materials are ideal for temporary magnetism application, such as in the moving iron application. Okay, fine. So in this case, the torque is not proportional to current, but is proportional to current square. We'll see the equation of the torque and other things in more detail when we will discuss this moving iron, but for the time being, the torque is directly proportional to current square. Okay, so basically it is not I, it is I square, means that the scale has to be non-linear. Okay, but the advantage of this system is they can be used for both AC and DC. We have just seen that moving coil kind of instrument are only suitable for DC kind of signals. Okay, so they are very simple and not very expensive. Okay, but of course they have limitation, like they are non-linear and there can be eddy current errors because you are using a conductive material. Okay, they are used in AC, DC ammeters and voltmeters. Okay, another kind of instrument is that we are going to discuss in this course is the electrodynamic type of instrument. So this electrodynamic type of instrument is based on, again based on the magnetic interaction only. Okay, but in place of this iron and a coil, so you have basically two different coil itself. Okay, one coil is fixed and another coil is movable. Okay, but both are carrying the current. Okay, so this kind of device, as I have mentioned, that the interaction of their fields create a deflecting torque, and the torque is directly proportional to the multiplication of the two currents I1 and I2 in the, say, fixed coil and the movable coil. Okay, so the torque is directly proportional to the multiplication of these two currents. Okay, so they are again useful for AC and DC both applications, and they have actually, they are basically very much accurate for power measurements. Okay, however, they are limited by their low torque and their low sensitivity to external fields. Okay, but they are basically utilized as wattmeters. They can also be, of course, be used as ammeter and voltmeter, but their main application is in the wattmeters. Okay, then we have induction type of instrument that we will discuss in this course. Okay, this induction type of instruments are actually based on the electromagnetic induction. Okay, so when an alternating current passes through two coils, the current coil, say two coils, I am naming them as current coil, which is a basically a series coil in the system. We'll discuss what is a current coil and voltage coil or series coil or shunt coils, okay, when we will talk about the electromagnetic induction. But for the time being, let's assume that the device has two different coils. One is called current coil, which is also known as the series coil, while the other one is the voltage coil, or also called as shunt coil, okay. So you are passing two different AC currents through this, okay. Now two alternating magnetic fluxes are produced, say they are phi 1 and phi 2, okay. Now the interaction between these fluxes and induced currents create basically a torque which is proportional to phi 1 multiplied by phi 2. This is also multiplied by a sine factor of theta, which is the phase difference basically between the two fluxes. So now the torque is not only directly proportional to phi 1 multiplied by phi 2, but it is also multiplied by a third factor, which is the sine of the angle between, or the phase angle between the two fluxes. Fine. So that is the basic principle behind this induction type instruments, okay, and they are again used for AC energy and power measurement, and they are kind of very simple device and they are very much reliable, okay. Limitation is only can be used for AC applications, okay, and they are very much dependent on the frequency and the temperature, okay. Example can be, say, one induction watt meter or some induction based energy meters, etc. Okay. Now next device is the electrostatic type device, which is also very important in this course, okay. This electrostatic type of devices are based on the force between two different charge plates, okay. So when two conductors at different potential are placed near each other, an electrostatic force of attraction develops between them due to some electric field between these two plates, okay. The torque in this case is directly proportional to the voltage square, and since there is a square term associated, the scale is again non-linear in nature. All right. So we have one more kind of device, which is the thermal type of device, okay. So again, as the name suggests, they are based on different thermal principle, okay, and they vary based on the principle or variation in the principle, okay. So the idea is when an electric current passes through a conductor, heat is generated. This generated heat follows Joule's law, which is H equal to I square R into T, where the H is the heat produced and I is the current which is flowing through the conductor, and R is the resistance of the conductor, and T is the time for which you are allowing this current to flow, okay. Now the heat produced of course causes the temperature to rise, which is then converted to mechanical motion of a pointer, okay, through the expansion of the material, okay. So the basic idea is the Joule's heating, okay. So most of these thermal devices are based on Joule's heating, but that is not only one principle. There can be multiple principle of this thermal type of devices, okay. So again, the application is in the measurement of high frequency AC currents, the true RMS measurement in power system, etc. Okay. So the heating effect instruments are primarily of two main type based on how they convert electrical heating into a measurable mechanical deflection. So basically based on the operating principle, you have basically two different type of thermal analog meters, okay. One is the hot wire instrument and the second is the thermoelectric instrument, which is also known as thermocouple instruments, okay. So we will discuss the working principle and other things of these instruments in more detail. Right now we are only discussing about their principle of operation, okay. So in the hot wire instrument, when an electric current passes through a thin wire, it heats up and expands, as we have just seen in a generic thermal type instrument, okay. The expansion of wire is proportional to the square of the current which is flowing, okay, and this expansion is used to move the pointer over a calibrated scale, okay, and this movement is basically because of the deflection torque. So the torque is being generated by the expansion, which is in turn because of the thermal or the heating because of the current flow. Okay, so basically you are measuring the current but through a indirect method. Okay, the application of this hot wire based devices like say hot wire ammeters and hot wire voltmeters you will find in laboratory. Okay, again this kind of devices can measure both AC and DC because both can generate this heating effect. Okay, and they are very much useful in high frequency measurements as well. Okay, the second kind of thermal devices are the thermoelectric or thermocouple type of instrument. Okay, so what happen that when a current passes through a heating element, it produces heat that we have already seen. Okay, the temperature difference at a junction of a thermocouple produces an EMF. Okay, this EMF is actually proportional to the RMS value of the current. Okay, now the current to be measured is passed through a small element which heats it. The temperature rise is converted to EMF by this thermocouple, okay, which is attached to the element. A thermocouple consists of a length of two dissimilar electric conductors joined at the end to form a closed loop, something like this. Okay, so this is at certain higher temperature, this is at a lower temperature. We will discuss about thermocouple, thermopiles, etc. when we will talk about the different transducers, I think in the next module. Okay, but for the time being you understand that this is a temperature measuring device, okay, which measure the temperature by measuring the EMF between the two junctions which are at different temperature. One is at colder, which one is known as cold junction and another is known as the hot junction, and this is again based on the thermoelectric effect. Okay, so a thermocouple is a temperature measurement device which operates based on the principle of the Seebeck coefficient or Seebeck effect. Okay, so it consists of two different type of metal wires or conductors that are joined at one end to form a junction, something like this, as I have already mentioned. Okay, when this junction is exposed to a temperature gradient, it generates a voltage which is proportional to the temperature difference. Okay, and this voltage as we know is known as the thermoelectric voltage. Okay, so the potential is given as the integration from T1 to T2, which T1 and T2 represents the temperature difference. Okay, and the difference between the Seebeck coefficient of the two materials. Okay, and integration integrate it with respect to dt from T1 to T2. So this will give you the EMF value. Okay. So if the junction of the two dissimilar metals are maintained at different temperature, a current will flow through the closed loop, and this current can be measured and is indicative of RMS value, as I have already discussed, okay, which is flowing through the heating element, and this is measured by the thermocouple itself. Okay, the application is again you can have a full-fledged thermocouple ammeters, okay, or thermocouple voltmeters, okay, and they are very common in RF and microwave measurements. Okay, the advantage is they measure the true RMS of any waveform. Okay, however they are limited by their slow response and their delicate characteristic. Okay, we will discuss about this thermocouple as I have mentioned in the transducer chapter, but in between we will also talk about the hot wire and the thermocouple based devices. Okay, next kind of device that we are interested in is the Hall effect type. I have already given a brief idea about this. Okay, so when a current carrying conductor or a semiconductor is introduced to a perpendicular magnetic field, something like this, okay, a voltage can be measured at the right angle to the current flowing path. Okay, so this is the current flowing path as already shown over here. Okay, so this effect of obtaining a measurable voltage is called the Hall effect. Okay, the Hall voltage can be given by this formula. VH is given as B into I by NED, where B is the magnetic field strength, okay, I is the current flowing through this material, okay, and N is the number of charge carriers per unit volume, okay, and E is the charge and D is the thickness. Okay. So the Hall coefficient can also be mathematically given by this E, which is the induced electric field divided by the current density multiplied by the magnetic strength. Okay. So just imagine that a thin flat strip of semiconductor which is carrying a current I is shown. Okay. When this strip is placed in a magnetic field which is perpendicular to the current, the moving charge carrier, be its electron or be its hole, depending on what kind of semiconductor it is, this will experience a Lorentz force which is given by F is equal to Q V cross B, right. Now this force will deflect the charges to one side, building up a potential difference, which is of course the Hall voltage across the opposite faces. Okay. Now this voltage is proportional to the product of magnetic field and the current value. Okay. Now this voltage is used as a measurable quantity when you try to make a analog meter based on this Hall effect. All right. This kind of device is used for magnetic field and current measurement, and they are suitable for DC and AC applications. Okay. You can also meet Gauss meters or current sensors based on this Hall effect. Okay. The advantage is you can do contactless measurement. Okay. And the limitation is they are temperature sensitive and require calibration at different stages. Okay. Then finally, we have another kind of device which is the chemical type. Okay. And this kind of device is based on the electrolysis. Okay. So basically what is happening is an electric current is passing through an electrolyte which causes its chemical decomposition. Okay. And the amount of substance deposited is proportional to the total charge. Okay. Now when current passes through the electrolyte, ions actually move towards the electrodes and a chemical reaction occurs. Now in these reactions, metals can be deposited or they can be dissolved in the electrolytes. Okay. Now the amount of substance that is deposited is proportional to the current value multiplied by the time value. So the total charge means if you know the total charge and if you know the total time, you can of course find the current. Okay. So the total charge can be calculated from the amount of chemical change which is observed in this chemical type instruments. Okay. So in this case, say if M is the mass deposited and Z is the electrochemical equivalent, this M is equal to Z into I into T, or M is directly proportional to current into time. All right. So this deposited mass is actually gives you direct idea of the current flowing. Okay. So they are used in calibration and energy measurements, but their use is limited, but they can only be used for DC applications, and the response is very slow. So they are very specific, utilized for certain applications, say a Coulomb meter or say electrolytic integrator and so on. But in general, the ammeter, voltmeter and other kind of devices which are available is usually not based on this chemical type. Okay, they always follow that moving coil, moving iron, etc. So we may have a limited discussion on this chemical type instruments. Okay, so if I summarize, we have seen different type of instruments like moving coil, moving iron. Okay, they were based on magnetic effect. Okay, the electrodynamometer kind of instrument were based on the field interaction, given there were two different coils. Okay, the induction kind of device were based on the electromagnetic induction or eddy currents. Okay, the electrostatic type of device is based on electrostatic interaction, which is based on the Coulomb force. Okay, then thermal kind of device is based on the heating effect. The heating effect can be a Joule heating, or you can also utilize a thermocouple for measuring that. Okay. Then we have Hall effect kind of device which is based on the Hall voltage. Okay, you can have magnetic sensor or current sensor based on this Hall effect, and then we have chemical type of devices which is based on electrolysis. Okay, and one of the major application of this chemical type of devices are the Coulomb meters. Okay, and their again utilization is very limited to the DC. Okay, so with this I think we have a good idea about different principle that is scattered among the different application of the analog meters. Okay, mostly we will confine our discussion in this course to moving iron, moving coil, electrodynamometers, induction type, etc. Okay, sometime we will go to electrostatic and Hall effect devices. Okay, so we will meet in the next lecture with some more kind of classification of this analog meters. Thank you.